Good morning to all of you. It's a pleasure to have you here. We are having today 3 lectures followed by an interactive session. Unfortunately, we are starting a bit late because of the traffic situation. So, without taking more of time, now Professor Vivek Datar, who is the project director of INO, is going to start today's sessions with talk title as the Neutrino, elusive but fascinating. He is going to take you through this wonderful particle called neutrino and why it is so difficult to detect, and what are the challenges, etc. And you will also, of course, talk about the INO project in which we are all involved, and what the week of which is actually being celebrated here. We can have another talk which is more of an engineering flavored talk on how the neutrinos are actually detected and recorded, right? So that's more of an engineering flavor. And this will be followed by another talk by Professor Urjit Yadnik from IIT Bombay. He's going to talk how the ultra small is connected to the extra large again. So he's going to again dwell on the neutrino and how it is connected to other areas of physics. And then we'll, as I said, we'll have at the end a very interactive session, following some quiz and some fun. And I see many of the younger people. I think that is the program today. But what we also want to tell you is that you can see a huge kind of bunch of things which are related to the detectors that we use for INO, and also the electronics and instrumentation that we are using for neutrino research in India, and particularly for INO experiment. So you'll be most welcome to come and interact with us and see things and ask questions about it. Okay, with this little intro, let me invite Professor Vivek Datar for his talk.
Okay. So let's start with this elusive particle called the neutrino. Before I actually begin, I would like to request you all to stop me at any point in time if you have questions. Okay. Of course, we will have you can ask questions at the end, but if something is not clear, you are most welcome to ask to break and ask me. Okay. So let me start with a poem by a well-known poet called John Updike. And this is just part of the poem. It's a pretty long poem, about 3 times this. Neutrinos, they are very small, they have no charge and no mass, do not interact at all. Not quite true, because we know that they have mass, it's a very tiny mass, nevertheless. But at the time that he wrote it, it was believed to be massless. And of course, they interact a little bit, because otherwise you wouldn't know of their existence. We wouldn't be able to detect them. The Earth is just a silly ball, which is true, to them, through which they simply pass like dust mites through a drafty hall or photons through a sheet of glass. Okay, with this poetic introduction, let me give you the plan of the talk. I'll introduce neutrinos and the phenomenon that was mentioned in the video, namely neutrino oscillations, which fetched a Nobel Prize in 2015. What is it that we want to do in India to have a neutrino observatory in an underground lab? What is the progress that we have made towards that goal? Mini ICAL at Madurai, and a very short summary. Okay, so neutrinos are elementary particles. By elementary, what you mean is that you cannot further subdivide them. This is the classic definition of elementary. So they are particles like electrons. So we'll come to that. There will be a so-called periodic table of particles, which is the next slide. So these particles were proposed by Pauli somewhat diffidently to explain the problem, to understand the problem in beta decay. In beta decay, we have a continuous beta energy spectrum, and at that time already quantum mechanics was known. It was developed in around 24 to 28, including relativistic quantum mechanics and so on. And so if you have definite initial and final states, you expect that if beta particles are emitted, beta particles should be emitted with a definite energy. However, the continuous energy spectrum observed led even scientists like Niels Bohr to produce a rather radical solution, namely that the laws of conservation of energy momentum and angular momentum are not obeyed in beta decay. That's a really radical approach. However, Pauli proposed a more conservative approach, and he said that, okay, maybe there is a third particle which carries away energy momentum. So depending on how this sharing occurs, the beta particle can have different energies, and indeed it can have a continuous energy spectrum. But he was a bit diffident, so he was to attend a conference. So he just wrote a letter to the organizers saying that, I have a very important thing to do. I have to attend a ball in Vienna, dance and so on. And he just wrote this letter saying that this is the solution that I propose. Of course, that solution turned out to be right. In fact, very soon after, Fermi, who took it very seriously, wrote a paper on that. He wrote basically a quantum mechanical theory for beta decay in 1934. Just soon after, Piles and Bethe actually computed or estimated the interaction cross-section, which tells you what is the mean free path and therefore what is the probability that it interacts in a certain amount of matter. This is a beautiful article for other reasons as well, because it uses just dimensional arguments. It's just almost a single column paper in Nature. And they calculated this using the minimal information that you have. That's you have typically MEV energies in beta decay with the Q values, and lifetimes of the order of 3 minutes. So these are the only two pieces of information that are used, and dimensional arguments to give you a cross-section which is 10 to the power of minus 20 of the typical nuclear cross-section. The nuclear cross-section, as you know, is measured in terms of barns. Okay, that is what? 10 to the power of minus 24 square centimeter. Correct. So this is 20 orders of magnitude smaller. So of course, at the end of the paper they write, therefore it is too small to detect. Okay? But as soon as a theorist says something like that, there are experimentalists who challenge it. And indeed this was challenged, and Reines and Cohen challenged it. Of course, they first thought of using the Manhattan Project to detect the neutrino, because of course when you have a bomb explosion, you have a lot of fission fragments coming out, and you get a typical time signature because it comes only at that time. The only problem with that approach, as was pointed out by another Nobel laureate who later won the Nobel Prize, Luis Alvarez, who was in Berkeley, he said that, so what happens if your experiment goes wrong? Can you repeat it? You can't. So then, taking another advice of another great gentleman called Fermi, who's mentioned here, they went to a reactor. Indeed, the reactor was making plutonium for the bomb. So there are two approaches in the Manhattan Project. Enrich uranium to have sufficient quantities of U-235 fractionally, and then plutonium. So there was already a reactor built for that purpose, and they chose to go to the reactor. And about 20 years later, in about 53 to 56, they managed to detect the first electron type of neutrinos. Of course, these are the photographs of the people involved. This is, of course, Pauli, this is Piles, this is Bethe. Bethe became famous, of course, for many things, including nuclear reactions that power the sun as well as stars. Of course, this is the great Fermi. Okay, so the electron type of neutrino was discovered by Reines and Cohen in 1956. They wrote up a seminal paper in Science, which is the premier journal at that time, apart from Nature. And for that, Reines got the Nobel Prize in 1995. Cohen was no more by that time, so of course he couldn't. People who are not there, who long passed away, they don't get Nobel Prizes. That's the Nobel Committee's rules of the Nobel Prize. The nu mu, which is another type of neutrino, another flavor or another family of neutrinos, that was detected for the first time in 1962 in not a reactor but in an accelerator experiment. That was the so-called alternating gradient synchrotron 26 GeV at Brookhaven National Lab in the US on the East Coast. And these three gentlemen, so Schwartz proposed an experiment using pions, and there is a slide later, if you have time we will go through it. But you produce an unstable particle called the pion in proton and nucleus collisions at high energies. Lots of pions are produced. Pions decay to muons and the corresponding neutrino. So his idea was that, is that neutrino the same as the electron neutrino? And indeed it turned out that it was a different type of neutrino. So we'll come to that. So this was the first experimental evidence for which they got the Nobel Prize in 1988, the three gentlemen here. Finally, of course, the last family of neutrinos was the nu tau, the neutrino corresponding to the tau lepton, and that was discovered in 2001 at Fermilab. So this is the so-called periodic table for elementary particles. So all the matter and radiation that we know of, that we see in the universe, the so-called visible universe, I should say, because there is also this dark matter and dark energy. So which constitutes about 4% of all that we know in the universe. All of that can be understood in terms of these, as far as we know. There are some smoking guns, but we'll come to that if at all later. So the strongly interacting particles consist of quarks. By strongly interacting, I mean neutron and proton strongly interact so that they bind in a nucleus, right? Otherwise, if you have protons in a nucleus, they repel. But the strong nuclear force overcomes that and allows the nucleus to be bound. So nucleons, such as neutrons and protons, are not elementary. They actually consist of quarks. So there are, for instance, a proton consists of 2 up quarks and 1 down quark. It's a three quark system. These are somewhat strange in that they have 2/3 of charge. U has plus 2/3 of charge and D has minus 1/3 of charge. So if you want to make a neutron, you have to take a U quark and a DD quark. So then that is neutral, electrically neutral. But this is the U, D and the electron are the ones with which the matter that we know, stable matter, is made up of, right? Atoms are made up of neutrons, protons constituting the nucleus, and electrons around that. But there are other families. Just as there is the nu mu and the corresponding lepton, the leptons interact only through the weak interaction or through the electromagnetic interaction. So the charged leptons, of course, interact through the electromagnetic. The neutral ones, the neutrinos, they don't interact through the electromagnetic interaction because they don't have charge. And also, as far as we know, they don't have any magnetic moment. Okay? For instance, the neutral particle, the neutral neutron has a nuclear magnetic moment, and that's in fact used in condensed matter physics to study structures which contain mainly hydrogen. Okay, so this is the second family of leptons, and the third family is the nu tau tau. The tau is much heavier. It's about 1.8 GeV. That's about 2 times the mass of a proton, and therefore it decays. Similarly, the muon is about 100 times 100 MeV, so about 10 times smaller than the mass of the proton, and it also decays. But of course, since the mass is much lower, it decays with a much longer half-life of about 2 microseconds, 2 odd microseconds. So these are the particles that constitute all the matter that we have, albeit unstable matter sometimes. But the forces between these particles, they are due to the mediation of these so-called force carriers. So when you exchange a photon between 2 charged objects, that gives rise to the electric repulsion if they are both positively charged, attraction if it is their opposite charge. So the photon is the one responsible for giving you the force between charged objects, electrically charged objects. The gluon similarly is the one which is responsible for the strong interaction between the quarks. Okay? The difference between the gluon and the photon is that the photon is only one type of photon. Gluons, there are 8 types of gluons. So this goes by the name of the theory for electrodynamics, goes by the quantum theory goes by the name of quantum electrodynamics. The theory for strong interactions is quantum chromodynamics. It's called color because they carry color charge. Color is of course just a name. You don't have to worry about it. There are 3 colors, and you could have given it some other name also. Okay. Finally, the weak interactions, which are the ones which make the neutrinos interact with matter. They are mediated by 3 bosons. The Z boson, which is an electrically neutral boson, and the W plus and W minus boson. These are about 80 times proton mass, and the Z is about 90 times proton mass. Okay? So these are the ones which mediate the forces between all these elementary particles. There is also this important particle which was discovered in 2012 at the Large Hadron Collider, which made news all over. So it was discovered at CERN, and this is the particle that is, we believe, gives mass to these particles. When I say to all particles, all except probably the neutrino, because in the so-called standard model of particle physics, the neutrinos are supposed to be 0 mass objects. Okay, so in fact, so in the so-called standard model, the electric charge of neutrinos is supposed to be 0. The mass is supposed to be 0, but experimentally we have right now an upper bound. It has to be lower than about 2 electron volt by c squared. Neutrinos only interact with matter through the weak interaction. And this, how weak is weak? weak is about 10 to the power, at least 10 orders of magnitude smaller in strength than the electromagnetic interaction. But of course, the dependence versus distance is also very different. This is the weak interaction, because it's mediated by massive bosons, goes like a Yukawa interaction. So it goes like e to the power of minus some constant times r. Whereas electromagnetic interactions go like 1 by r to the power of n. So they decay much slower than exponentially decaying interactions. So of course, there's a big difference between these. Okay. A fundamental property of the neutrino, whether it's its own antiparticle or not, even 90 years after it was proposed, we do not know the answer to that. And there are experiments being conducted to find this answer. So if the neutrino is not its own antiparticle, then it would be called a Dirac neutrino, and you would require 4 complex numbers to describe it, just as electron wave function requires one complex quantity, the psi of r. Of course, we might be varying with r and so on. Okay, so in this case, you have 4 components. On the other hand, if it's a Majorana particle, which is its own antiparticle, then only spin is the one which defines it. There's no antiparticle part of the wave function or the spinner function. So there's a 2-component spinner, so to speak. So there are 2 numbers that describe it. So this is a simpler description, but we don't know yet whether what nature obeys is this or that. It's the second most abundant particle in the universe. Can anybody say what is the most abundant one in the universe? Most abundant particle in the universe? Pardon? Photon, yes, you're right. So the photon is about 400 odd particles per cubic centimeter all over the universe, okay? If you take an average for neutrinos, that's about 300 or so, 330 per cubic centimeter. So this is indeed, since it's so prevalent everywhere, of course we need to understand what its properties are. And as I said already, it provides a window to the beyond the standard model. Why? Because it has mass. Standard model doesn't give mass to the neutrino. Okay. Now, if you want to study neutrinos, of course, you have to get to sources of neutrinos. What are these sources? The sun is the most prolific one. In the tip of your finger, about 60 billion of neutrinos are passing every second. Okay, but you don't come to know of it. Hardly one may interact in your body over the course of your lifetime. So that's how weakly they interact. Okay. However, they do interact a little bit, and that's why you have to make big detectors and count for long times. Then there is a nuclear reactor, of course, where it was indeed discovered. The anti-neutrino was discovered at a nuclear reactor in a nuclear reactor experiment. Particle accelerators produced them, just as the new mu was discovered. Then there are other sources like atmospheric neutrinos. So we know that we are bombarded by cosmic rays from extra galactic, galactic and so on, but protons coming from various reaches of space. Okay. And they interact with the upper atmosphere. The Earth, fortunately, is covered by an atmospheric sheath which protects us from these cosmic rays, as also other things like small asteroids and so on. And when the cosmic rays interact with the upper atmosphere, they are mainly protons, as I said. They interact with oxygen, nitrogen nuclei, then they produce particles called pions. Okay? They are, again, strongly interacting particles, but they are composites of quarks. They are like UU bar, DD bar, such objects. When these are produced, they are about 140 times the mass, 140 MeV or so, that means about 270 times the mass of an electron. They decay, and they decay to muons and neutrino of the muon type. Typically, they have lifetimes of the order of 26 nanoseconds and so on. So once they decay, they produce mu and nu mu. Then the muon also decays, as I said, with about 2 microseconds half-life. So then that further produces electron, 2 neutrinos, one of the muon type, one of the electron type. So in an atmospheric event like this, cosmic ray interaction and so on, each of these pions leads to 2 muon type of neutrinos and 1 electron type of neutrino. What is the importance of this we'll come to. This played a major role in the discovery of neutrino oscillations. Then there are other sources like supernova. Supernova is a thing that happens when a star explodes and leaves an inner core, which could be either a neutron star or a black hole. In this process, electrons combine with protons to give you neutrons, and that's why you get a neutron star sometimes at the end. If the mass is, of course, larger than about 10 solar masses, then it makes a black hole. And you have all heard in the newspapers about a few years ago, black hole collisions occurred and they collapsed into a single black hole and the gravitational waves were detected. So these supernova emit about 99% of the energy released through neutrinos. And indeed, in 1987, we managed to measure these neutrinos on the Earth in a terrestrial experiment. Again, I will have a slide on that. Finally, we believe now that the universe came about as a result of the Big Bang, and this Big Bang led to a very hot soup of quarks and leptons and photons and so on, and then they formed nucleons, they formed various particles, and when they decayed, you got also neutrinos, but also initially in the Big Bang, in the hot soup, there were neutrinos. Now when the universe expanded, these neutrinos occupied all of that space, and there should be, as I said, about 300 odd neutrinos per cubic centimeter. Of course, they are at a very low energy. Their temperature is of the order of a couple of Kelvin. So they are in the region of about 100 or 200 microelectron volts. They are extremely hard to detect. If somebody actually finds a way of detecting them, this is absolutely sure to fetch a Nobel Prize. Okay, then how does the neutrino interact with matter? It interacts in various ways, but the most common one, which allows you to actually identify what the neutrino was, which type it was, the electron type, muon type, or tau type, is the so-called charge current interaction. So it's called the charge current quasi-elastic reaction. For example, nu mu interacts with the neutron to give you a mu minus and a p. And since the mu minus is much lighter than the proton, it carries away most of the energy. Just as in beta decay, for instance, the electron and the neutrino carry away most of the energy, the recoiling nucleon carries away very little energy. So this is the way you can actually identify. So if a nu E comes in on iron, and this is the material that we are going to use in our ICAL at INO, then it forms a cobalt nucleus and gives out an electron. And the charged particle is what you detect, because you cannot measure or detect, let me say precisely, a uncharged particle as such. It has to undergo some reaction, produce a charged particle or many charged particles, and then those you can measure. There are other reactions, like for instance elastic scattering. Nu E can scatter off an electron. Oops, what's happened now? Let's come back. Okay, so this is called elastic scattering. In this particular case, of course, there is not just the neutral current interaction, because a neutrino can come in, go out as a neutrino, an electron can come in, go out as electron. So what is exchanged is not a charged boson, but it's a Z0. So the heavy boson is Z0 is exchanged. So that's called a neutral current interaction. If a neutrino comes in, goes out as an electron, and a W plus is exchanged, then that's called a charge current interaction. I don't know why this is happening. This is happening a little more frequently, I think. Okay, so these are the various, oops, this is maybe cable is a problem. There's a video cable somewhere, no? Okay, so let me just say that there are various processes with various probabilities depending on the energy of the neutrino, but for a typical energy, let's say of 1 GeV, which is 1 followed by 9 zeros, 10 to the power of 9 electron volts. This is why I say this energy, because this is the kind of typical energy that we will be detecting. This is in fact the threshold of our ICAL detector at INO. Okay, so for that, if you compute or estimate the mean free path, that is about 10 to the power of 9 kilometers, in iron. So the probability of detection in the detector that I will talk about is about 50 meter by 15 meter by 15 meter by 16 meter. That's about 2 into 10 to the power minus 11. And this implies, for the given flux of atmospheric neutrinos, which is about between 1,000 and 10,000 per second per square meter, it comes to the order of magnitude estimate is about 10 per day. Now, cosmic muons are all bombarding us at the rate of about 200 roughly per meter square per second. This is per day. In a day you have typically about 10 to the, how many seconds? Anybody? About 10 to the 6 seconds or so. So on such a 10 to the 5 maybe, 10 to the 5. 3 10 to the 7 is a year, and 300 times less than that. So it's about 10 to the 5. So 10 to the 5 seconds, 200 per meter square, and we have a 1000 square meter area you can compute. This is a humongous background. Okay, so you can't do this experiment over ground. So I will come to that. Just remember this, that this is of the order of a few or 10 per day, such a low rate. Okay, now I come to, this is one of the most important discoveries that was made, namely neutrino oscillations. So let me just give you a kind of background to that from a quote by Bacall, who was a very leading neutrino scientist and also a leading astrophysicist of his time. So the statement is that solar neutrinos have a multiple personality disorder, Jekyll and Hyde. You'd be Jekyll and in the night you would be Hyde, right? So transformation of personality. So these have a multiple personality disorder. They are created as electron neutrinos in the sun. He is talking about solar neutrinos, and this is a possible explanation for that. But on the way to the Earth, they change their type. It could be in the sun, it could be in vacuum. Oops, again. Okay. For neutrinos, the origin of the personality disorder is a quantum mechanical process called neutrino oscillations. In quantum mechanics, if something can occur, it will usually occur. Okay. So, for instance, a nu mu, to start with, suppose you have a nu mu, it can become, with some probability, a nu tau or a nu e, or indeed remain as a nu mu. And at a given oscillation length, it can go back to nu mu. Okay. So, this is the kind of scenario which you have for oscillations. What is the experimental evidence? We have experimental evidence from atmospheric neutrinos. As I said, there should be about 2 to 1 muon type of neutrino to electron type for atmospheric neutrinos. Now the Earth, as I said, is covered on all sides by the atmosphere, and neutrinos can penetrate, much more than the Earth itself. So the Earth is basically transparent to neutrinos. So neutrinos from the other side of the Earth will also reach your detector. Now you would expect that this ratio of 2 should be there for whichever be the direction of the neutrino, right? What was observed was something surprising. The ratio was 2 for downgoing neutrinos, but was 1 for upgoing neutrinos. So what is the reason? One possibility could be that the nu mu becomes some other type of neutrino which is not getting detected. Okay, or nu e somehow increases in number. But either of these explanations would require some transformation of these neutrinos among themselves. This is the most conservative kind of explanation of this data. Other than saying that maybe they decay. The nu mu can also decay to something which is not seen, but as it turns out, this oscillation explanation is the correct one. And since this does not depend upon the absolute number of neutrinos that are produced, you don't have to care about what kind of interaction the proton has with the nucleus, what is this cross section, what is that branching ratio. This is fairly robust, because as soon as you produce a pion, you produce a muon, then this ratio will be as it is. Okay, so this provided the first evidence for neutrino oscillations. This was published in 1998 and fetched, as I said, a Nobel Prize in 2015. There was also this solar neutrino detection, which was done by Davis and company right from the early 60s, mid 60s I should say, and he continued his experiment for almost 25 to 30 years, very painstakingly. He was a radiochemist by training, and he collaborated with John Bacall, the same Bacall that was mentioned earlier, who was the theoretical physicist, who actually calculated, based on the so-called standard solar model, how many neutrinos you expect. And this experiment observed a shortfall. And this was the explanation of neutrino oscillation was actually proposed by Bacall as satisfying the observations. This was poo-pooed initially, but then ultimately he turned out to be right, and Davis also got the Nobel Prize. Okay, then we will come to this also in some other context, that the Sudbury Neutrino Observatory in fact went one up on the Davis experiment by doing an experiment in real time with 1 kiloton of heavy water, extremely pure heavy water. So they borrowed this for $1 from the Canadian Heavy Water Agency, and of course purified it and then gave it back after the experiment was over in a much better with a much better purity to the same heavy water agency in Canada. Then there are reactor neutrinos, of course. They have been seen, the oscillation phenomena and its effect on the neutrino spectrum has been seen in a 1 kiloton liquid scintillator detector in the Kamioka mines. Finally, of course, accelerator-based nu-mu disappearance experiment has been done in MINOS. Now there are several ones of that type, NOVA, then the J-Park to Kamiokande and so on. Okay, so let me just start out telling you what is meant by neutrino oscillations. That was just a verbal, picturization. Neutrinos, for instance, can be described in two ways. Base is just another word for two ways, okay? It can be described in so-called flavor basis, that means whether it's of the E-type, mu type or the tau type, or it can be described in terms of its mass, M1, M2, M3. And if these are different, then these two so-called representations or descriptions, you might say, have to be connected by a matrix. It's a unitary matrix, okay? It can have complex components. So this is the way it is connected. A flavor basis state is connected to the mass state or set of states through a matrix like this, okay? And since there are three flavors, it has to be a 3 by 3 matrix. But you can do this thing, you can describe what really happens just using two flavors. Two flavors, the simplification is that you just need one angle to describe the mixing. It's just like you have a coordinate frame and you rotate this coordinate frame and you ask, how can I describe a vector, let us say, in one basis as compared to the other Cartesian basis? And there is a connection between the two. So if you do that, if you work out the quantum mechanics, which is not very hard, but I'll just tell you the result. The probability that a muon type of neutrino remains a muon type of neutrino, that means this is the, it's a disappearance measurement. Why disappearance? Because it goes like 1 minus sine squared some angle, 2 theta, and sine squared another quantity, which depends on the length that it travels and on the energy of that neutrino. And another very important quantity, delta m squared. Delta m squared is the difference in mass squareds, okay? Now you can see that the probability that it remains a nu mu depends on sine squared 2 theta, the deviation from 1 depends on the finiteness of sine squared 2 theta. So if sine squared 2 theta is 0, then this quantity is 1, whatever be delta m squared. Similarly, if delta m squared is 0, you can see because it's a sine squared something 0, that will also be 0. So you get, so if you start out with a muon type of neutrino, it will remain forever a muon type of neutrino, if either of these two quantities is 0, okay? The fact that this deviates from 1 therefore means that both of these quantities have to be non-zero. Theta has to be non-zero and delta m squared has to be non-zero. If delta m squared has to be non-zero, can both masses be 0? No, at least one of them has to be non-zero, right? One of them can be 0 or both can be non-zero, okay, that's allowed. Both non-zero or one of them 0, one of them non-zero, both. These two situations are allowed. But as I said, if this deviates from 1, it means that neutrinos have a non-zero mass, okay? That's the basic message that I wanted to convey. Now, of course, the real situation is slightly more complicated. Instead of 2 flavors, you actually have 3 flavors, and therefore that becomes a 3 by 3 matrix. And then just as you have a Cartesian frame with 3 axes and you rotate it, then there are 3 Euler angles. I think the engineers would probably be familiar with that apart from the physics people. So there are 3 angles that are required to describe it. And it turns out that all these 3 angles are non-zero, okay? It also turns out that delta m squared is not all that small. I mean, it's tiny, but it's not very tiny. Okay, this is one. The second thing I want to say is that just as when a photon passes through glass, it interacts with the medium, it polarizes the medium. And what is the effect of that? You get a refractive index, because the changing polarizations interfere with the main photon, and they cause, it looks as though the photon is moving at a speed smaller than that of light in vacuum, okay? Now, this interaction part is sort of similar in the neutrino case. When neutrino goes through matter, it interacts with it, and it effectively changes these mixing angles, as well as the masses, the delta m squareds change. Now, what is the effect of that? Forget about, this is not too complicated an expression for a two flavor mixing. The sine squared of 2 theta is related to sine squared of the theta in vacuum, but divided by this quantity, delta 21 cosine 2 theta minus a, where this a is some quantity proportional to the density of electrons that this neutrino encounters and to the energy of the neutrino. Now, if delta 21 is positive, look at what happens. A is positive for neutrinos, but A is negative for antineutrinos. So let's take the neutrino case. A is positive. If delta 21 is positive, when these two quantities match, then this becomes 0, right? And then the numerator and denominator are the same, so you get sin squared 2 theta equal to 1. So even if you were to start out with a very small theta, you end up with an effective theta in the medium which is 1. So this is called a resonance. So this is a resonant oscillation that happens. And this was the proposition of Wolfenstein. Did somebody come to try to see where the cable is trying to? This is happening quite often now. Namely that the neutrino, as it traverses different densities in the sun is most dense in the core, and the density drops as a function of radius. So somewhere along the line, this resonance condition will be satisfied for neutrinos. And if delta 21 is positive, then this will happen and they will oscillate away into the other flavor. Now, if the other flavor cannot be detected, indeed it cannot, because through the charge current interaction it has to produce a muon, and the energy of these neutrinos from the sun is hardly a few MeV. Okay? So it cannot create a muon. You violate conservation of energy. So it can't do that. Now, therefore, you will see a shortage of electron type of neutrinos. And this is very robust, because depending on the energy, this will happen at different densities. But it will happen. It's guaranteed to happen. So this was proposed in an explanation, and in fact it can be turned around, and if you see a shortage and attribute it to this, then you can even tell what is the ordering of the masses. That the way it happens, M2 is greater than M1, and this is the conclusion. So after looking at other experiments as well, this is the conclusion that is drawn. So this gives you the order between M2 and M1. We'll come to why it is important. Okay, so now let's go back to atmospheric neutrinos. As I said, this I already have said. Atmospheric neutrinos were detected at SuperKamiokande. Actually, by the way, they were detected for the first time in the Kolar goldfields by an Indian group. This was in '65, and the paper was published on a nice day for India, the 15th of August, 1965 in Physics Letters. So this was a discovery by the Indian group. They had a collaboration with Durham University and Osaka State University. And in fact, they beat the Nobel laureate Rhines to it. Of course, he was quite close. He published it in PhysRev Letters about 2 weeks later. But this is a very important discovery. Unfortunately, we didn't follow up on that. We went to look for proton decays, and then ultimately the KGF closed down. And these experiments couldn't have been running the KGF on their own, and that's why that program had to stop. And also, unfortunately, protons don't seem to decay. If they had decayed, again, somebody would have won a Nobel Prize, because the KGF experiment was the first one to get off the ground. So if the lifetime of the proton was 10 to the power of 29, as Pati and Salam had proposed, then somebody, as I said, would have got a Nobel Prize from the Indian group. But that didn't happen. And now in these proton decay experiments, so many other experiments were set up, including one at Kamiokande. So it was called, the first experiment was called Kamiokande detector experiment, looking for proton decay, and then they built an even more massive one because they didn't find proton decay. So they said, okay, let's go bigger, and they built this 50 kiloton water Cherenkov detector. They didn't find it yet. In fact, to this day, we don't know if the proton decays or not. We don't have any evidence of its decay yet. But on the other hand, the background for that experiment was ultimately neutrinos, because neutrinos, as I said, can come from any place. I mean, they can penetrate the whole Earth. They turned that background into a signal, and indeed they measured atmospheric neutrinos. So, for instance, the nu mu can be detected through a Cherenkov ring. What is Cherenkov light? Just as a supersonic plane, when it moves in, let's say, in the say 30,000 or 50,000 feet above the ground, it leads to a sonic boom, and you can hear it. Some of these Sukhois or MiG-29s and so on, they give the rise to the sonic boom. Similarly, when a charged particle moves with a velocity close to that of light in vacuum, it is moving actually in that medium faster than light in that medium. So that gives rise to a light boom, and that's the Cherenkov ring. So Cherenkov light is emitted in a cone, and so if at any given instant it emits Cherenkov light, you project it on a screen, you get a ring. Of course, as it goes along, it produces different rings, right? Because as the distance becomes closer and closer, the ring becomes smaller and smaller. But you can project it back in time. You have also temporal information. So if you project out a certain slice in time, then the muon ring is sort of sharper than the electron ring. Electron ring, you can see many of these counts here, because the electron is a light particle, it can scatter. Okay, so the Cherenkov light, the cones are slightly different, and so you get a scatter on that ring. So you can use various methods, techniques, and the ones have been refined now to identify muons from electrons. And this is exactly what I said. They see that you expect a ratio of muon to electron type of neutrino as 2, but you observe for the downgoing ones 2, but not for the upgoing ones. And this has led to the Nobel Prize, as I said. And oh, by the way, it is also important that it's not just the water. Of course, it is even more important to have the sensors to detect this Cherenkov light. And these are done by photomultiplier tubes, which were actually, constructed for this experiment. In fact, I heard just the other day that the Koshiba, who got the Nobel Prize for detecting, of course, supernova antineutrino, but who was responsible for making the Kamiokande 3,000-ton water Cherenkov detector, he actually convinced Hamamatsu, that's a name, to make such photomultipliers. And initially they were not so excited about this possibility, but he happened to be, it seems, a few days or few weeks senior to him. And in Japan, like in India, you respect the elder, and so if the elder says that you should do it, then he does it. And that's how he developed this massive photomultiplier. This photomultiplier tube is like this, 0.5 meter in diameter. Nobody had made such photomultipliers before, but they developed it and they led to fantastic results. Okay, so now I come to solar neutrinos. As I said, the sun is powered by nuclear reactions, and these nuclear reactions are, some of them are given here, but I just want to point out everything ends at about A equal to 8, and to go beyond that you require to do something else, and that's where the contribution of Fred Hoyle came in. He proposed the state in carbon-12 is called the Hoyle state, but this was a set of reactions proposed by Hans Bethe, and for which again he got the Nobel Prize in, I think, 68 or something like that. But notice the first reaction. The first reaction is proton plus proton goes to deuterium, which is a combination of proton and neutron, a positron, the antiparticle of the electron, and a neutrino. Since a neutrino is there, obviously there has to be a weak interaction process. And because it is weak, the sun lives for as long as it does. Okay, it's expected to live for another 10 billion years probably. But had it been an electromagnetic or strong interaction, it would have died in hours or days. Okay, so there wouldn't have been the life on Earth there wouldn't have been time enough for life on Earth to evolve. It would have just died. It would have become a dead star, like a white dwarf or whatever. So because of this weak interaction, so the neutrino is playing a crucial role. If the neutrino is not there, we wouldn't know life as we know, and secondly, we wouldn't have anything on Earth to speak of. Okay, so but how do we know that all this is happening? I mean, this is a good theory, no doubt. Bethe had a very nice theory, but how do we know that it actually happens? So the evidence you have is things that can probe the center of the sun. And what particle can do that? Photon cannot do that, because photons you only see from the outer surface of the sun. What is going on inside you cannot probe. The only particle that can probe it is if gravitation were there, graviton. But of course nothing like that is happening on the sun, so is the neutrino. And this is in fact a direct product here. So if you detect neutrinos, then you have evidence of fusion reactions. And the number of these neutrinos can be calculated fairly robustly, because you know how much is the energy that the sun emits. You know which these fusion reactions, how much energy is released, and you can actually calculate. Roughly there are 3 neutrinos for this reaction to happen, so you can calculate that. And of course these neutrinos have a rich spectrum. PP neutrinos dominate, they're 90% of all the neutrinos, but there are higher energy neutrinos like the boron neutrinos, which contribute very much to the chlorine signal, and I think that is in the next slide probably. Okay, I think I showed this. So Davis did this experiment using a chlorine-37 detector in the Homestake mines, and the solar neutrinos are expected to produce only 1 atom in 2 days. So he irradiated for a week, flushed out the argon, put it inside a very low background counter, proportional counter, counted it, and did that, and kept doing that for about 25 years. You can just imagine the kind of patience that is needed for this, the strength of will that is needed, because there are all people saying that, oh, it's very difficult to detect. No, you can't detect it. And even if you find it, how do you know that it's not background and so on? So anyway, he persisted and showed that this is, so the summary of that is shown here, that he actually measured a number with this error. So in some units called SNU, he he had a number which is about 1/3 of what was expected. Of course, there are other radiochemical experiments like the SAGE and GALEX. They also measured a number which was about half, but this was different because this experiment was sensitive to PP neutrinos as well. So this is the first radiochemical experiment which showed that PP reactions also take place, because if they didn't take place, this signal would have been lower. Then the Kamiokande, of course, they were originally measuring atmospheric neutrinos, but they lowered their threshold to about 5 MeV or so, 4 to 5 MeV, and then were able to measure the solar neutrinos from the sun. And since they did elastic scattering measurements, so they could even point back to the sun. So you can actually take a picture of the sun in neutrinos now. Of course, it takes quite some time to do that. So I don't have a picture here, but you can see a picture of the sun, which took about 15 years to do. Whereas if you just take a camera, you can do that in 1/2000th of a second. Okay. Now, the Sudbury Neutrino Observatory, on the other hand, use a heavy water detector. I will not go into the details, but through the neutral current, you can actually break up deuterium. Deuterium doesn't have too large a binding energy, only 2.2 MeV. Okay? So you can break up deuterium into neutron and proton, and then you can detect the neutron. If you go in deep enough in the mine, backgrounds for producing neutrons can be controlled. And that's what exactly they did. And the neutral current is essentially sensitive to all flavors of neutrinos. So if a nu E goes to nu mu, it can still be detected through this reaction. Goes to nu tau, still can be detected. So now in the same detector, they have a Water-Cherenkov signal from the nu E, but they also have a signal from all the neutrinos. Now, what is the shortfall is made up if you look at all the signal. So they conclusively showed that neutrinos oscillate. Okay, it's a beautiful experiment. And this also, in fact, fetched the Nobel Prize in 2015. So the 2015 Nobel Prize was shared between the person who contributed most to the SuperKamiokande experiment, but also to the Sudbury Neutrino Observatory. Okay, now I should. How am I doing in time? Almost over. Okay. So I will not go over the reactor neutrino experiments, but as I said, you can do this as an exercise. A typical 1 gigawatt electrical, take about a 30% efficiency, so it's actually 3 gigawatt thermal. It emits about 6×10 to the power of 20 neutrinos per second. It's a very strong source of neutrinos. So if you go close enough, you can detect it. That's what Reines did. Okay, but you can use it now for other kinds of experiments, and the way you detect it is antineutrino plus proton goes to positron and neutron. Then you detect the positron both through the energy deposit of the positron. Positron has energy, it loses its energy in the scintillator, let's say, and then it also annihilates against the electron to give you 2 511 keVs, so you detect that as well, and then it emits a neutron which is a low energy, it's about 10 keV or of that order. That you can thermalize. If you have a hydrogenous medium, you can thermalize that. You can get captured on gadolinium. Gadolinium has a very large cross section, at least 2 isotopes of them. And with a small amount of gadolinium, you can capture them, and then that produces a typically 8 MeV signal. So that high energy delayed neutron signal can be used to kill almost all the background, and therefore you can produce spectra. So this is a figure which shows, the way the emitted spectrum is, the way the cross section for interaction of the neutrino goes like E squared at low energies, and a product of these two, when you fold this, you get this kind of a spectrum measured, and this is indeed the spectrum measured. So this can be used, for instance, to measure one of the mixing angles, θ13. In fact, it has turned out that that is the most accurately measured neutrino parameter. So what happens is, if you go further and further away from a reactor core, then you should observe remaining an electron type to go down, then oscillate with a high frequency component which corresponds to one of the delta M 2 3, and then or 1 3, and the other one which is the delta M 1 2. So if you have the right distances, you can probe all of this. You can probe this, which probes mainly θ13, but you can probe this as well, which is coming from here, θ12. And this has also been done by, again, a Kamland experiment, which is a 1 kiloton liquid scintillator. So they have to float it in some buffer oil so that this doesn't collapse under its own weight. And they have measured actually the modulation of the reactor antineutrino spectrum. This is due to oscillation. But an outcome of that, and this happens, this is very well suited because the detector which was placed in the Kamioka mine, that happened to be roughly 200 kilometers away from all the reactors that are there. There are a few reactors which are off scale, but most of them are around 200 kilometers. So this helped. That means L by E is, L is at least a similar thing, a similar number. And another unexpected outcome of this was that they actually measured geoneutrinos. Neutrinos occurring from the decay of uranium, thorium and their daughter products. So for the first time, they could compare geological model produced neutrinos with measured neutrinos, and they agreed to within the error bar, about 25% or so. This is a Nature paper shown here. Okay, accelerator-based experiments, I think I will not have time to go. The basic idea is that you produce neutrino beams of nu mu such, and because of the kinematic focusing, because you have a high energy pion, it decays, so the neutrinos come focused in angle. So you can do this experiment hundreds of kilometers away, and this has been done in at least three places in the world. Fermilab to this Minos detector, about 740 kilometers as is shown here. So they pass through the earth and they reach the Sudan mines where this detector is, and then you can put a detector close by, so you can normalize, so you don't need even to know what is the flux. You do this by that and appropriately scale the distance, then you can see whether there is an oscillation signal or not. So there is this near detector, 1 kiloton near detector and a far detector, and so they have a result which shows oscillation. So it's a ratio of observed neutrinos with respect to energy versus no oscillation. So it shows that indeed this oscillation. This would have been 1 if there is no oscillation throughout, but you can see that for certain energies this goes down almost to 0. That means almost all the neutrinos are converted to neutrinos of the other type. That's because the large mixing angle close to 45 degrees. So then sin squared 2 theta becomes sin squared 90, which is about 1. Okay. So as I said, it turns out from all these experiments that there are two scales of delta m squared. One is the so-called atmospheric scale, which is about 30 times larger. So we know the ordering of M2, M1, but we don't know the ordering of M3. It could be higher or it could be lower. This is called the normal and this is called the inverted hierarchy. How does this become important? This becomes important because in accelerator experiments which are trying to look for so-called particle-antiparticle asymmetry, which is what is responsible for why we are here. There is, unless particle-antiparticle asymmetry is there, we won't be here. Because if there are equal number of particles and antiparticles produced in the Big Bang, they would all finally annihilate, there would be only radiation, photons and other particles, mainly photons. Okay. So the fact that we are here means there is a small asymmetry. That means slightly more particles are produced. So if you have 10 to the, let's say, 10 to the 20 particles and 10 to the 18 antiparticles, then 10 to the 18 annihilate, but there are 100 particles left. And that is what produces the universe that we know of. Okay. So in experiments searching for that type of particle-antiparticle asymmetry, accelerator experiments actually have a problem because they combine this asymmetry, which is governed by a parameter called CP violation, and delta m squared. Now if you don't know one or the other, you can say it is because of this if this is so and so. If it is normal mass hierarchy, then you have this delta CP. If you have inverted hierarchy, then this is delta CP. Whereas if you know the hierarchy, and this is our USP for the ICAL, then you can tell what the CP violation is exactly, or within error bars of the experiment. Okay, I will not go into this. This is, oops, I don't know whether it's a problem with this one. Okay, so we hope to build this India-based neutrino observatory where we hope to measure these atmospheric neutrinos in a detector, huge detector about the size of an Olympic-sized swimming pool, 50 meters long, about 16 meters wide, and about 15 meters high, and about 51 kiloton of iron, 51,000 tons. It will have layers of iron and RPC, so-called resistive plate chamber glass detectors, which detect the muons and give its position x, y, and the layer number gives the z. So the position is identified, so the track can be built, reconstructed, and then you can reconstruct what the neutrino energy ought to be. Okay, so from this you can, and since neutrinos and antineutrinos, as I said, interact differently with matter. Okay, depending on the ordering, you will see one of them affected, but the other one unaffected. Okay, so if mass ordering is one way, neutrinos will be affected. So the spectrum that you see will be modulated by that. There will be a dip or something like that. And in the other one, you will just see a smoothly falling spectrum. Whereas if it is the other way around, in the antineutrino spectrum, you will see that, the same thing. So we can use this to get the ordering. So in about 6 years' time, along with other experiments, we hope to fix this at the 3 sigma level. Now, of course, this is not the 5 sigma level, which is supposed to be the gold standard for instance, LHC experiments. But 3 sigma is already pretty high probability. I think it's something like more than 99% probable that this is so. So once this is there, then the accelerator experiments can say that, okay, delta Cp, which is the parameter that tells you about particle antiparticle asymmetry, what it is. Is it 0 or is it non-zero? The problem is that Cp violation has been seen in the strong sector, through hadronic decays, meson decays, but that's not enough to explain this. It's much too small. So we are looking for other sources where this might be violated. And neutrinos have been violating things left and right. Parity is violated, lepton number is violated. Quite possible that Cp is also violated. Particle antiparticle symmetry is also violated. So this could be a potential discovery in the waiting. Okay, so this is the big collaboration of about 28 institutes all over the country. Why do we need a huge magnet? As I said, neutral particle cannot be detected as it is. But once it makes mu plus or mu minus and you can track it, then knowing the direction, which can be done by timing, I think Satya may talk to you about it, then you know which direction is coming, then you can tell what is the track, because if you have a magnetic field, it will bend oppositely in that. Okay, so that's the reason why you have an electromagnet, and that's why this is the largest electromagnet that we will hope to build. Why go underground? Because of cosmic muons. There are two ways of doing it. You can do it in a mine or in a tunnel. Tunnel now is the favored approach because you can take trucks and carry huge equipment in that. Mine, you are restricted to roughly about 2 to 3 meter by 3 meter. Now we have plates which are 4 meter, we have coils which are big. So the logistics tells us that tunnels are better. Indeed, the pioneering lab was the Gran Sasso lab, and now all labs in the future I think will go like that. Unless you have a very tiny experiment. If you have a tiny experiment, then mines are still good. Okay, so these are the experiments that are planned. You probably saw that some part of it in the video film as well. Neutrinoless double beta decay search. These are in the R&D stage right now, and the dark matter search led by the Science Institute. This is led by the TFR group, and a low energy accelerator is also proposed for nuclear astrophysics. This is the scheme. As I said, I'll not get into this too much because I'm already a little late. The good thing about atmospheric neutrinos is that it provides a whole range of energy because there is a continuous spectrum, 1 to 20 GeV, and range of propagation lengths. You can look for neutrinos going down or from the bottom. So, and they are free, of course. The downside is, of course, that there are not too many in number. You don't know the precise energy. You have to measure it. Okay. So the USP of this is that we can get the mass ordering, but there are other things that this can do. And for instance, mixing parameters, you can look for magnetic monopoles, which is a completely unsolved, nobody has yet found evidence for magnetic monopoles. This would symmetrize the Maxwell equations. We can search for anomalous KG events. This is also an open problem. These are some strange events that were seen in the Kolar gold fields in the proton decay and atmospheric neutrino detection era. You can look for a sterile neutrinos, long-range interactions, or whatnot. There are many other things that this do. So while this is one of the important problems, there are many other important problems. And quite often it happens that what you think is important may not be the one which you finally do, actually. So just as I said, the proton decay experiment actually gave a Nobel Prize for neutrino research. It was completely unexpected. Okay, so we decided to build a mini ACL. There are various goals of that, but I'll just show you some pictures. So this is a 4 meter by 4 meter, so go back to that. This is a 4 meter by 4 meter by 11 layer toy, so to speak, as compared to the 17 kiloton module. We have 3 17 kiloton modules planned. So this is almost 1 by 200th of that. Just 0.5% of that one single module. It's very tiny, but it gives us an opportunity to learn a few things. And also it gives us measurements of cosmic muons, which could be compared with some simulations that were done by colleagues and so on. And we will also do other things there. If there are questions, I'll be happy to answer. So, for instance, the plate machining was done in Bhilai. So these are various shapes, various sizes plates, 56 mm thick magnetic grade iron, low carbon steel. And then these things have to be spaced out by spacers and held by pins. And then you have to have an electromagnet, so you have to have a conductor which is carrying current up to about 1000 ampere. So these conductors, we use the same ones which we are going to use finally. So it's about a 30 mm square cross-section conductor with a hole in it to provide for cooling water, pure deionized cooling water. A lot of time was spent in actually straightening these out. These came twisted, and so finally the central workshop in BRC, they did a great job of it. And the coil was done in two parts, a U, which is bigger, and then a C. And so you assemble the U's first, put the plates, and then after all the plates are put, then you braze the C's together, and then you can pass current through them. Of course, they have to be tested for leaks and resistance and so on. They satisfied all those conditions. Okay, so these are some pictures here. These things were standing on a pillar. And the plates these U's were first erected. Then the plates were put in place, so you can see assembly going on using a gantry crane. And then after everything was done, then the Cs were put on top and brazed using an induction brazing machine. So you can see here that the C is being brazed to this, and there is the hole which is ultimately will carry water, cooling water. This is the low conductivity water cooling system for the magnet as well as the power supply that drives the current. These are some places where you put magnetic field measurement devices. So Hall probe, many of you are familiar with that. So we have a strip which has about 15 of these Hall probes, and we can put such strips at 10 different places on 3 designated layers out of the 11. And then we can measure the gap magnetic field, which gives you also a measure of what is the field inside the magnet, inside the iron, which is what is needed ultimately when you want to calculate how the muon tracks. This is the power supply. This is an old supply which was, one card was bad, this was refurbished. And these are the places where you also put coils, pickup coils. So this uses the Faraday effect. So if you change the current, you change the magnetic field, you get an EMF, and then you measure that. And so there are 2 alternate ways of measuring it. They're also trying a third method of stop muon, whose spin can rotate. And so using a perturbed angular correlation technique, whether we can get any information at all. We've still not come to getting any number yet, but it probably has promise. Okay, so the glass gaps were made in industry, 2 meter by 2 meter glass sheets, separated by 2 millimeter, and sealed off using spacers. So that I think maybe Satya will show, or maybe not, I don't know. Then there is a gas system, because there is a slightly special gas, not very special, but 95% of freon which we use in refrigerators, and some little bit of isobutane, and then SF6 to quench things. But since this gas is, a lot of gas is required, about 200 meter cubed of gas is the inventory in the detector, so you cannot afford to just throw it out. And also it's bad for the environment in the sense that it is a, what is that called, greenhouse effect gas. Both SF6 and freon. So there is a closed loop system which has only a very small amount of leakage goes out, and that's it. The electronics is all basically designed in-house by colleagues like Satya and colleagues in BRC. So they have made all these boards that are meant for this, for detection, for high voltage, and so on. Even designed ICs, so-called ASICs, application-specific ICs, got it made in a foundry elsewhere. Finally, when all these detectors were assembled, 10 layers of detectors were put at the center, and this is how it looks. It looks very neat. Here you have the people who are, some of the people who are involved in that. Also, we did a lot of outreach in the sense that lots of summer students came. At one point, I think there were up to about 30 or 35 students from various universities, from colleges, and so on. And their feedback was that they benefited. So students here as well who want to come there in the summer are most welcome to do that. We even give you a small token honorarium, okay, for helping you survive there. Okay, so finally, of course, you want to see tracks, right? All this is meant to see muons, because the new mu induces a muon. And of course, in cosmic rays, you have muons of either type, mu plus, mu minus. So you can see oppositely bending tracks. This is the so-called non-bending plane, so you can see almost a straight line. So almost, why? Because at lower and lower energies, you can't fix the energy of the muon that you get from cosmic rays. So at lower energies, there is more scattering of muons from the iron nuclei. So there is some deviation from exactly a straight line, but is more or less straight. Okay, so this is the non-bending plane, whereas in the bending plane, the magnetic field affects the trajectory. So the X plane is the bending plane. So this is at about 900 ampere, where you expect a field of about 1.4 Tesla, which is borne out by the Hall probe and pickup loop measurements. That's all. I think I'll end here. This is the mountain where we hope to build, and where we hope to make a tunnel at the end of it. Right now, of course, there's a problem in the Tamil Nadu government is not very, initially it was very cooperative. Right now it is not all that cooperative. So we have plan B and so on. But again, I can on a one-to-one basis tell you what is the plan that we have. On the other hand, it's quite possible that they might change their attitude, and we might really go in thinny. Thank you.